All right, good morning, everyone. Welcome to Hydrogeology, GEO 420, April 7th, Zoom lecture. Okay, so let's talk about what I'm hoping to get accomplished today and how I think the day is going to go. So first of all, we got to try to figure out the test scenario, what the test is going to look like. So I've been playing around with various options for the test. I looked at a Moodle quiz format for the test. I don't think it's really going to work for us. So what I think I'll do is I'm gonna give essentially a test that looks a lot like I would have given it had we been in class. I will give you guys an extended amount of time, so probably 3 hours to finish it. Some folks who have DSS modifications will get a little longer than that to submit. And the test format will be pretty similar. So I want you guys to, you'll have to print the test out and take it. And it's going to require some writing and some drawing. So you need to be able to print. You need to have your pen and paper. Okay, so there's a lot of stuff out there on how to try and proctor an exam in Zoom. And some people are suggesting you guys try and set up a camera on the paper, and I try to assess whether you're cheating or not. Here's the bottom line. We're just going to pretty much take this honor code. I'm going to let you guys do it open note and open book. But here's the thing, because I just can't proctor it. Here's the thing. Right now, every one of you is thinking, sweet, I don't have to study. All right. You cannot study for the test and get all the assignments or questions done during the test time. All right. Don't think that's going to happen. You have to study, or else you won't know how to approach the problem. You're not going to have enough time to go through all your notes, figure out how to solve the problem, and solve the problem. So study, just like it's not an open note, open book test. Otherwise, you're not going to have enough time. I will probably, modify the questions to be a little bit from what I did previously, just because you'll have access to notes, but you're going to get the same materials. I'm going to give you the equation sheet, and it's going to be pretty similar. So the big things for you guys are going to be able to print and then turn that PDF in. All right. So you got to be able to do those two things. Does anybody have problems doing those two things, printing and then turning a PDF in at the end? Okay, if anybody does, just send me an email at some point, and we'll try and figure out a way around it. But I'm hoping that we can figure out how to do that for everybody. Okay, I plan on spending probably this, I'm going to lecture here for a little while longer, and then I'll go over, the content of the test, and then open it up for you guys to ask me questions about the test. So if you've got questions about content or format, let's get into them after I lecture a bit. Yeah. Any other business up front I want to cover? Not really. I think that's going to be it. So in that case, let's there's one more subject I wanted to cover before we review for the test. And that is freshwater, saltwater interactions. So I'm going to share my screen here and we'll start talking about freshwater and saltwater interactions. Okay, so salty water and freshwater interact in a variety of different settings in hydrogeology, but obviously in coastal zones for sure, where you have the ocean and the terrestrial groundwater system adjacent to each other. Many of these interactions also occur even in terrestrial settings, because the deeper you go in groundwater systems, the more likely you are to encounter saltwater. So typically groundwater that's below a few hundred meters tends to start to get to be pretty salty. And when we're down a kilometer or two, often we're in very saline brines. And so there's lots of places where we need to consider the differences in density and how that affects our groundwater flow system. So we'll talk about this generally from the coastal hydrogeology perspective, because that's more typically the problem, but a lot of these principles still hold for deep groundwater, where you have brines and freshwater possibly interacting. Okay, so the first thing we're going to start doing is thinking about the interface between freshwater and saltwater. And so to do that, I'm just going to draw a picture of some coastline, and we've got the ocean. So saltwater is going to be green. So I've got the ocean, and here's the land surface. All right, so underneath the land surface, we've got a water table. And the water table is gonna basically rise to the level of the ocean. And then beneath the land surface, there's some interface. So we'll call this the saltwater interface. So on this side, we've got freshwater. And on the other side of the interface, we have saltwater. And generally, this interface is pretty sharp. All right, so surprisingly, the waters are fairly immiscible. And so you'll often get, over the space of a meter or two, you'll change from freshwater to saltwater. And so a lot of what we're interested in is the location and the depth of this interface. Because if we want to put a well in, all right, and we're interested in irrigating our crops, and we're in a coastal area, all right, we want to make sure our well is above the interface and pumping fresh water, not below the interface and pumping salt water. So oftentimes we're interested in the location. The location of this interface is generally what we're after. And then how does this interface move if we do things like pump or change groundwater flow? How will the interface location change? So some of the things that can affect the location of the interface is the amount of groundwater flow, right? You might imagine that the more groundwater or the stronger the groundwater flow is towards the ocean, it might be able to push this interface towards the ocean. The thickness of the freshwater unit, if we've only got a very shallow groundwater circulation system, then the saltwater will probably extend farther inland. How much water we're pumping, all right? If we're intercepting that groundwater flow, then seawater can intrude landward. And then things like tides and just the general geologic setting. So let's look at quantifying the location of the interface and getting more rigorous about this. So start a new page here. So the depth of the interface. So here I'm gonna draw another, zoom in a bit right on the interface. So here I got the land surface dipping down. Here is my ocean, all right? And here's my freshwater water table. And here is, I'm gonna make the interface red. Here is the location of my interface. And I'm gonna consider a point on this interface here. And let's say that this point, here is the height of the salt water, HS. And the height of the fresh water above that point is going to be equal to HF plus HS. All right, so the freshwater interface has this height HS plus HF, and the saltwater just has the height HS above it. All right, and if the fluid is not moving, that means that the fluid potential is the same. All right, and if I just make the datum of the point be my datum, so Z is equal to 0, then it's the pressure heads on either side of the interface have to be equal. All right. So if my interface is not moving, my pressure heads on either side of the interface must be equal. All right, so I can write the pressure head of the saltwater side is, all right, so I have my pressure on the saltwater side has to be equal to my pressure on the freshwater side. And I can write this as rho S G H sub S. All right, that's the pressure at this point on the saltwater side. And this has to be equal to rho F G times H sub S plus H sub F. All right, so the freshwater density now times the total height, which is H sub S plus H sub F. Okay, I can do some algebra and solve for H sub S because that is the elevation below sea level of my interface. All right, so H sub S is the elevation below sea level. The depth below sea level of our interface. Okay, so I can solve for H sub S here. That gives me H sub S is equal to rho sub F over rho sub F. Oh, sorry, over rho sub S minus rho sub F times H sub F. All right, so this equation allows me to look at the depth of the saltwater interface given the height of the freshwater above sea level. All right, so at any place here, if I know the elevation of my water table above sea level, I can predict the depth of the interface. All right, so for example, if I wanted to put a well over here, all right, if I know this height of the water table, I know how deep I can move my well can be before I hit the saltwater interface. All right, so I can keep my well away from the saltwater interface. So let's look at an example of this in practice, and this is the island example. So here we're gonna go to Hawaii. All right, we've got some island On either side, we've got the ocean. And under the island, we have a freshwater water table from precipitation. All right, and here is sea level, just as a reference. And at any place here, my freshwater saltwater interface is given by this equation, H sub S is equal to rho F over rho S minus rho F times HF. And so what you get is a inverted curve that's amplified. So our freshwater saltwater interface might look like this, where the height at any point here, or the depth at any point, all right, is given by star. This depth is given by star. All right, so this water here is called the freshwater lens. And it sits on top of this body of salt water. All right. And if we know the shape of the water table, we can predict the thickness of our freshwater lens. All right. So if you're a hydrogeologist practicing in Hawaii, this would be a principal concern of yours, especially since a lot of people want to build their homes or their hotels right here. Then it might be a real problem of trying to keep above the saltwater interface. Okay, so all of these examples sort of just consider a static interface and just using the height of the water table to predict the height of the depth of the interface below the water table. Let's now think about flowing water in a confined unit. So this is interface for a flowing well. All right, so I'm gonna zoom in on the shoreline. And I'm gonna add some stratigraphy now. So let's say we've got a confining layer at the land surface. And then we've got a confined aquifer. And another confining unit here. And for now, let's say that our sea level is coincidence with the boundary, upper boundary of our confining unit. And that we've got a water table that slopes, or a potentiometric surface, not water table, that slopes upward in our aquifer. So this is the potentiometric surface of the confined aquifer. All right, so at any place here, we have H sub F, that's the height of our potentiometric surface above sea level. And what we're interested in here all right, is the location. And in particular, we are interested in the inland distance. So this would be X, the inland distance of our interface from the shoreline. All right, so we have at some X, we're going to have HS, the height of the saltwater or the depth of the saltwater below the below sea level, and then we'll have HF, the height of the freshwater head above sea level. Okay, so a few things here, other things that we're going to want to define. So our aquifer thickness is B. And now let's consider what flow in our freshwater aquifer looks like. So flow through our freshwater aquifer is given by Darcy's law. K A delta H delta L. All right. And let's break this up. Q is equal to K A, which would be at any one point. So let me consider this point P. At any point, the discharge through the aquifer above that point would be given by the area of the aquifer above the point. So Q at P would be given by the area is H sub S times W, some width in and out of the board, times delta H over delta L. All right. And I'm going to divide by W. So I'm going to get Q prime at P is equal to K H sub S delta H delta L. All right. Where this is Q over W. All right. Okay, let's make some other definitions. Well, now let me consider our equation for the saltwater interface at X, all right? So first of all, I can write, let's think about what H sub F at X would be. If this is a straight line, Well, actually, let's think about what delta H is. All right, delta H over delta L. I'll just do that. So delta H over delta L here at X is equal to H sub F minus the height here of the freshwater or of my head above sea level at sea level is 0 over delta L is X. All right, so I can put that in here, and now I got Q prime of P is equal to K HS times HF over X. All right. We can solve this now. For H sub S, H sub S, do some algebra, is equal to X over K times HF. Times Q P prime. And now we can remember that H sub, we can insert our equation for star for the relationship between H sub S and H sub F, and we can get this final statement. So insert star. Rho F over rho S minus rho F. Q prime over K H Q prime times X over HS. So finally, I'm going to write this equation. X is equal to rho S minus rho F over rho F K HS squared over Q prime. So this equation right here gives me the distance the inland distance x of my saltwater interface, all right, given the depth below sea level that I'm interested in. All right. So if I was to go 100 meters below sea level, I know how far inland my interface will be. All right. And it's a function of the groundwater flow through our aquifer. Okay, and then finally, if I wanted to go to my full depth, so if I insert B, all right, which is my full aquifer thickness, I'm going to get my maximum length of intrusion, all right? So the max intrusion will be at the bottom of the aquifer. And so we put B in here for H sub S, and we're going to get L is equal to rho S minus rho F over rho F times K B squared over Q prime. All right, so these equations can help us think about a few things. And some interactions that are common. So if we go back to a drawing here, all right, and so here's our system. Here's sea level. Here is our interface. All right, and we have groundwater flowing basically through our confined aquifer. And essentially what it does, it flows through here and it discharges out to the surface. All right. Okay, so here's our interface. The location of the interface is a function of this discharge, Q. All right. So if I put a pump in here, so let's say I'm building a hotel in Hawaii. All right, and I put a pump in here. And I start pulling out water, all right, out of my aquifer. First of all, what do I do to the discharge? If I'm pulling water out of here, what am I doing to the discharge in the aquifer at the interface? If someone answered, I couldn't hear.
You said you're lowering it.
Yeah. If I'm taking water out of my aquifer, it's no longer discharging to the at the interface, so I've reduced Q prime. All right, if I make this a smaller number, what's going to happen to the location of my saltwater interface?
move inland more?
Yeah, it's going to move inland. All right, so if I pull Q out, I reduce Q prime, my saltwater interface moves inland. All right, and this process called saltwater intrusion. And this is one of the principal problems in coastal areas and coastal hydrogeology, is trying to understand where and when saltwater intrusion is occurring and how to mitigate it. All right. So one of the things that, so saltwater intrusion is a huge problem, like in places like Florida, where in Florida, you've got a lot of people. Almost all of them use groundwater. All the cities use groundwater for their drinking water supplies. And so they've drastically reduced the discharge to the ocean, and the saltwater interface has intruded. In many places, it's intruded until they start producing salt water, and they're no longer able to use fresh water from those wells. So one thing they've been doing is taking their wastewater. So they use their water and then they drill another set of wells near the coast. All right. And they inject wastewater. Right. By injecting the wastewater here, they now increase Q again and move the saltwater interface back out. All right. So this is one way that people combat it. You pump inland, but you re-inject your wastewater back into your aquifer near the interface and try and drive the interface back out. There's one other really important kind of saltwater intrusion, and that is from upconing. And here, let's just consider our island example. All right, and we had this freshwater water table, and then our interface between the two looks something like this. All right. So if I put a pump in, say here in the middle of my island, and I start pumping out groundwater, we're going to talk all about this, but essentially what we do is we induce what we call a cone of depression around the well. And you can think about this intuitively. In order for groundwater to flow into my well, I have to reduce the head in the well so that the water will move from high potential to low potential. All right. So I have to have this cone of depression in order to pump. All right. And the shape of this cone of depression, and how rapidly it sort of propagates out into the aquifer, we're going to talk a lot about, because that's a principal way we investigate the properties of the aquifer, is to look at how this cone of depression forms and how it changes as a function of the pumping rate. But for now, let's just say once we start pumping, we induce this cone of depression. That is, the water table lowers around the well. Well, if my water table height lowers, what happens to my interface underneath the well? So if I think back to this equation, H sub S, which is the depth of my interface, is equal to rho sub F over rho S minus rho F times H F. If this guy, so here, because of my cone of depression, that means that H sub F gets smaller around the well. So if this gets smaller, what happens to the depth of my saltwater interface in this equation?
It would decrease.
Yeah, H sub S then goes down. So that means that you get this mirrored cone. All right, and this is my upwelling, or my upwelling salt water beneath my pumping well. All right, and you can, if you continue to pump, you continue to draw this cone down, you can get it so that the cone intersects your pumping well. All right, we can describe the location or the depth. We can describe this depth, H sub S, with an equation. We will learn how this equation gets, we'll learn the basis, but it's another equation for the shape of the water table, all right, around the well as a function of pumping. So this is Q over 2 pi D, where D is this guy, times K rho F. Oh, I'm sorry, that is not D. I'm doing the wrong equation. What else did I just erase? D is this guy. It is the, D is the original depth of the interface beneath the well, and H sub S is the new, H sub S is the new depth. So this is upconed, and this is original depth. Okay, so my upconed depth is a function of my pump rate. All right. Basically, it's a function of the pump rate. So the harder, the bigger my pump rate, the in fact, I've got this backwards. Sorry. Upconed height. I'm going to change. I'm sorry. It's just horrible, but you're going to have to live with my scribbling and changing things. Doesn't make sense to call this H sub S because we've been defining H sub S as the height beneath, or the depth beneath the water table. Z is the change in height, or this height of our cone. and D is the original height. So the more I pump, the higher Z gets, or the higher the increase in my cone height from the original depth towards my well is. All right. So basically what this says is the higher I pump, the higher this cone gets, and I can calculate what my maximum pumping rate is before I have my cone intersect my well and I start breaking through and producing salt water. All right, so this allows us to keep pumping rate low enough so Z doesn't intersect our well height, or Z does not equal to D. All right, so bottom line is that, yeah.
Just a quick question. So if D is representative of the original depth of Z, so before upconing, wouldn't Z and D intersect as soon as Z changes?
No, this is not your fault. It's my horrible drawing and continual scribbling. I need some new colors. It's a good question. And let me try and clarify. All right. So my the original depth to the interface was D, all right? So the original height from the bottom, from the interface to the bottom of my well was D. Z is now the new height after upconing, Z. So when Z equals to D, that means that my upconed well has come all the way up to the bottom of my well, right? Because if Z is less than D, the height from the original, this is basically the change from the original depth to the new location, is less than the total original depth. So as long as Z doesn't equal to D, I'll still be producing fresh water. But when Z equals D, that means this new height from the change from the old water table or the old interface to the new interface is exactly equal to the original depth of the well above, or the original depth of the interface below the well. All right, so couple important things. So this saltwater intrusion happens via two mechanisms. You decrease the discharge, and then the saltwater can intrude inland. All right, and you also decrease or change the shape of the water table, and that allows the interface to upcone or upwell. The bottom line is the main way to combat this problem is to decrease the total amount of water that you're taking out. So if I decrease pumping here, then I'll decrease the upconing height. If I decrease pumping here, then I'll decrease the seawater intrusion height. If we have to use water, you know, for various reasons, then if we re-inject, we can sort of mitigate some of these problems and try and maintain the saltwater interface at distance from our extraction wells. Okay, so upconing, intrusion length, and then being able to describe the depth of our interface using this force balance equation. Those are the main topics that we're going to consider here for sea level or saltwater freshwater interactions. Okay, that's pretty much going to end my lecture on saltwater freshwater interfaces, although I'm happy to answer any questions, especially for the upconing one since I've flubbed the drawing. I also wanted to talk about, at the end of the day on last Thursday, we did those fracture flow or effective continuum calculations for fracture flow. The equation was right. And so basically, you know, the matrix at that fracture spacing, the matrix permeability or conductivity and the effective conductivity were much closer to each other. So any other questions about saltwater, freshwater interactions? All right, if you don't have any other questions, or yeah.
About like how dependent on time is that boundary line, like with tides?
How dependent on tides? So it is, in general, the interface will be at somewhere, let's say at high tide, you know, we're up here, and at low tide, we're down here. This would be my tidal changes. Our interface will be given by sort of the mean location. The interface itself doesn't change a lot with tides. And the reason why is because these tidal fluctuations in pressure won't propagate very deep into the subsurface. They don't have enough time to propagate very deeply. But it doesn't change a lot. Now, a lot of that depends on, say, the magnitude of the tidal change. But in most places, we don't worry too much about tidal influence. We worry more about the long-term shape and the steady state location of the interface.
Would it be also dependent on the K value? Like how readily that water infiltrates into it, or is that not as
Yeah, absolutely. It does depend on K. Look, K is in both these equations, K and K. All right, so it definitely depends on K, but in particular, it depends on the ratio between how much you're pumping and K. Okay, so it depends on the relationship between discharge and K. So in general, like, let's consider our upconing equation here. The higher my hydraulic conductivity, the lower my upconing height will be. So in general, I want my higher K is better in general. But in particular, it's the relationship between Q and K that we're interested in. All right, any other questions on saltwater, freshwater interactions? So, you know,
Is density sub S the density of the salt water or the density of the sediment?
this is saltwater.
Okay.
Yeah, use so for our critical, so for quick conditions, there's a very similar ratio of densities. And there we used rho sub S again, but it was the sediment density there. So for any of our Irish colleagues that might be on the line, I don't know that Ireland uses a lot of groundwater because they're wet and it rains all the goddamn time. But do you know, have you heard of saltwater intrusion problems in Ireland? Is that a problem? I know I saw
I don't
some.
think so.
You don't think so?
Yeah.
Not for me either. I haven't heard too
I
much or
haven't
anything
heard of it
really
being
about
a
it,
problem
especially
there.
'cause no, a lot of our water, especially like in Dublin and that, even though it's on the coast, it's taken from the aquifer below ground anyway, or from rivers. So I don't think we have much of a problem with the saltwater intrusion.
Yeah, my hunch is that because it rains so much, Q is high enough that no matter what you guys pull out, you're not changing the height or the discharge of the aquifer appreciably. And that's mostly just because it's, you know, a really wet place, so you're not water limited. But, you know, I would imagine in some places they have to start worrying about it, even in Ireland. Okay, let's take a couple minute break, and then I'll sort of switch gears and talk about the test, and sort of what we covered and what we should expect on the test. And then I'll leave some time for you guys to ask questions if you got them. All right, so let's take a 5-minute break, say 10 after 9, I'll start lecturing again. Okay, so I did a 2-minute Google search on seawater intrusion in Ireland, and did find one interesting article where they looked at sort of seawater intrusion by just measuring chemistry in a bunch of groundwater wells near the Galway Bay. And at any rate, just a couple things to highlight what we were talking about. Seawater intrusion was found to occur within 5 kilometers of the coastline. All right, so you had to be pretty close to the coastline. And there was some tidal influence on groundwater levels. Not necessarily on the chemistry, but on the actual level. If you were sort of really close to the coastline. And they talked about sort of how the extent of the seawater intrusion is dependent upon the hydrologic conditions, so how wet it was or what the discharge through the groundwater system was. All right, so just thought I'd point out that for our friends who are in a more coastal setting, people are trying to study where and when and how much this is occurring. You're lucky in Ireland because you get plenty of water. It doesn't appear to be a huge problem. Okay, so let's go to sort of test review or talking about the test. I'm not going to do a full on review, but I will talk a bit about what to expect, and then I'll answer questions. So first of all, the test will cover basically all the material from the first test until I don't think I'll probably put fracture flow or I won't put fracture flow or seawater freshwater interactions on there. So the big topics that we've covered, the first was we developed the groundwater flow equation. So the groundwater flow equations. All right, we talked about how to read these partial differential equations, what kind of system they might imply. So I'm not going to expect you to derive any of the groundwater flow equations, but I will expect you to be able to identify the proper groundwater flow equation for the proper system. All right. And we talked about these so we talked about how material properties or the properties of the aquifer might be put in there. Homogeneous versus heterogeneous. Isotropy versus anisotropy. We developed them for confined, unconfined, and variably saturated systems. All right, so you should know the difference between the confined aquifer equation, the unconfined aquifer equation, or the Boussinesq equation, and the variably saturated equation, or Richard's equation. What else? Oh yeah, steady state versus transient. All right, so again, you need to be able to identify the correct equation for the correct type of flow system that we're attempting to simulate. All right, so one of the things that we talked about is how do we use these groundwater flow equations? So a big thing that I want you guys to at least know the basics are, what are the ingredients to solve? So ingredients, to solve the boundary value problem. All right, so in order to simulate groundwater flow, the first thing we need to understand is the sort of the equation that describes that type of flow in that setting. But then we need to think about how do we actually solve that partial differential equation. And in order to do that, you've got to have some basic ingredients. And so I want you guys to know what those basic ingredients are. And then we talked about some simple solutions. So an example of that is flow nets. All right, expect to see some flow nets on your exam. All right, so understand the rules of flow nets. Rules of construction. How do we use them to, so understand how we analyze them to get things like discharge or head. Effects of heterogeneity. All right, so, you know, be able to draw flow nets and for a variety of different settings, and then you know, understand how we analyze flow nets to calculate properties of interest for a groundwater flow system, such as discharge through the flow net. Okay, we had some other simple analytical solutions. So understand what an analytical we talked about various analytical solutions, but for example, one was one analytical solution we talked about was for the Boussinesq equation, where we had sort of a system with two rivers at different heights. And it was receiving recharge. And it had a water table. And we thought about where the water table divide might be. All right, and we also talked about an equation that gave us the shape of the water table. All right, I'm not necessarily highlighting this particular analytical solution, except that we talked, you know, we threw out a few of these. So I want you to understand like what an analytical solution is. All right, and that draws, you know, a connection directly between these two. And, you know, when be able to properly identify a solution to your problem. So an example might be is I might ask you, say, well, find the water table divide here, because I want to know whether contamination is going to this river or to this river. Right? That might be your question. Well, we had another analytical solution that sort of described the propagation of the head change. If I change the river stage here, how does that move out into the aquifer? That analytical solution doesn't really help us solve a problem where we're interested in flow and the location of a groundwater divide. So you need to know the setting that these solutions are applicable for, and then be able to apply them to solve your problem. So this is the key. This is like sort of in a nutshell, the key to solving the boundary value problem is understanding what ingredients you have and then what solution fits those particular sets of boundary conditions, governing equations, and you know, properties. Okay, so the other big thing that we hit hard since the last test was unsaturated flow. All right, so, you know, I would definitely understand pressure head, you know, above and below the water table. You know, understand what characteristic curves relative permeability, you know, I would expect you to be able to calculate some of these things. So I might say, you know, I would expect you to be able to take, say, a measurement of volumetric water content. Well, first of all, I might expect you to calculate this from field data. And then be able to back out psi and relative conductivity. All right. I might expect you to calculate unsaturated flux. So this is really, you know, unsaturated Darcy's. All right, so this will be the meat and potatoes of the exam. Essentially, since the last exam, you've done one homework assignment. All right, and so I would definitely be able to understand how to do every one of the problems on that homework assignment. And the big sort of 4 topics would be sort of the groundwater flow equations. How do we solve boundary value problems, flow nets, and unsaturated flow. Those are the sort of big topics that, you know, I can foresee putting on the test. So we've got, you know, another 20 minutes here. Do people have questions, specific questions they want to discuss about any of these topics, about the test in general? You know, yeah, go ahead.
Justin, when you were saying to know the homeworks and all that kind of stuff, will you be popping out a key for that just in the meantime, just so we can double check what we've done?
Yeah, I was hoping to be able to turn the homeworks back today. We will get them back either today or early tomorrow, and we'll have a key
okay.
Posted. And so you should be able to check your homework, see what you did right, see what you did wrong, and use that as a study guide. And those should get back to you either later this afternoon or early tomorrow.
Can you go over quick conditions again?
Sure. Let me actually see if I can find my notes on the subject here. The bottom line is quick conditions, much like our saltwater interface, is a force balance. So we're seeing whether the gradient in fluid pressure is enough to essentially float the sediment. And so quick conditions. If we sort of do a bunch of force balances, then we can come up with this relationship. The rho sed minus the freshwater row water density over row water is equal to the critical hydraulic gradient. So delta H, delta L. This is actually delta Z, critical. All right, so if my gradient in head, my vertical gradient in head is greater than this ratio, then I will be able to float my sediment and I have quick conditions. If my hydraulic gradient is less than this critical value, then I won't be able to float the sediment and I won't have quick conditions. So is that
A direction associated with the critical hydraulic gradient?
no, it's just a value. There's a direction. It has to be vertical. Like when we did our force balance, basically we're balancing the force of gravity with sort of the upward buoyant force from water. So we're balancing sort of pressure and gravity. So the direction really is vertical. It needs to be a vertical head gradient. Versus gravity. So this guy here is your dH, dz. It is the head gradient in the vertical direction, right? That you need to calculate, and you need to compare it to this critical value. Does that make sense?
Yeah.
Okay, other questions?
As far as just the timing and everything, is there a time that you're gonna post it and a time you want it turned back in, or?
I mean, that's a really good question. Mostly because I'm not sure how to do the timing. I will post the test at 8 Thursday morning.
Okay.
I'm not sure if in Moodle I can then say you have to turn it in by 11. I think I can do that. I think what I'll do is create an assignment. So let's say this. I'm going to post the test at 8, just like a normal test. And you will have 3 hours to turn it in. Now, I have some other folks who, you know, I need to give longer times to, and I'm not exactly sure how I'm going to handle those exceptions. If you've got a problem, either with the test time at 8 in the morning, or you need more time, then you just need to communicate with me and we'll make accommodations. But my thought is just to try and keep this as similar to a normal test as possible. So I'll post it at 8 or maybe a little bit before, and you'll have to turn it in by 11 Mountain Time.
Maybe just a little bit longer if you have to print it and then rescan it to upload.
Yeah, so I'm given another hour, so 2 hours. So I'll try and make the test be basically a normal length, which is somewhere like an hour and 50 minutes. And then you'll have another hour to figure out how to scan and upload it. if you're having problems, again, just let me know and we'll make modifications.
Okay, perfect.
I will be, let's also say this, I will be on Zoom at 8 in the morning, Thursday. And so any questions you have, please just log into the Zoom meeting, because, you know, if you've got a question, other people are going to have the question, and then I can, you know, broadcast it to other people. Let's also you know, say that this is my first online test, and I don't know how many you guys have taken, so I'm not going to be trying to make this really difficult. My point here will be as accommodating as possible and try and maintain the test as close as possible to the original design. But, you know, if we need to make modifications on time, if things aren't clear in the test, you know, we'll adapt to those conditions, and just know that my philosophy of the test is not to figure out how to take points away from you. It's just to try and get the assessment in that the course was designed to have. So so I'll try to be as accommodating as possible. But please communicate with me if you're having problems understanding something. You know, communicate with me, and I'll try and make sure that those questions get broadcast to everybody so that everybody has a chance to get that clarification. Okay. Well, if no one, you know, I'll hang out for the next 10 minutes, but if you guys don't have any more questions, then feel free to bug out if you want.
Hayden, when can we expect to have access to our homeworks?
Good question. I need to, Kimberly hasn't responded to me, so I don't know where she is in grading, but I would, you know, by tomorrow morning at the latest.
Okay, thank you.
So if I can print out the exam, so how should I deal with the problem? So should I type the writing by word, or I don't know?
You can't print out the test.
I don't have any. Yeah.
I think what you can do, if you can't print the test, this probably goes for everybody. You don't necessarily have to print the test out. You can just write your answers on another sheet of paper.
By myself.
Yep.
And is it possible to draw from it by using the PowerPoint, like class?
I'm sorry, Junior, breaking up, so I couldn't understand.
So maybe we probably will supposed to write the format.
Yep.
So in this case, is it okay if I use PowerPoint to draw the format, like last class?
I
I don't know.
I'm trying to think about it. The problem is, I think that will take yeah, the place where it'd be nice to print is for the FlowNet so that you can get the domain. If you're not going to print, then you have to figure out how to draw the FlowNet on the computer in some fashion. So PowerPoint would be fine, or any other program. What I want turned in is a PDF. So, you know, if you draw via PowerPoint, then you got to convert those images to a PDF.
Okay, thank you.
Okay, thanks, Peyton. I'm gonna head off.
Yeah, sounds good.
Thanks. Bye.
Yeah, I don't have any further questions. So thanks. Have a good morning.
Yeah, you too.
Is there going to be like questions like similar to 5 about like plotting certain graphs about certain different soil types or anything like that on the test? That was really with 5B. I just couldn't figure out like how to set up that problem. And
I'm not gonna have you guys plot a characteristic curve in the test. I mean, that's not something that's can be done in a test, but I would expect you to be able to calculate relative conductivity and pressure head.
could we go over like a quick example of how you would do that, or like go about that?
Sure. So like you know, one question might be calculate the pressure head psi given theta sub W equal to 0.7. Not 0.7. Equal to 0.2 n equal to 0.3, theta sub r equal to 0.05. And given, you'd be given things like lambda and psi b. All right, so we got this, we got a couple things. So Brooks Corey, so let's just, SE is equal to theta minus theta sub r, theta, or sorry, n minus theta sub r, and then SE is equal to theta sub b, or psi sub b over psi to the lambda. All right, so first of all, I'd have to calculate, I'd have to take this guy, this guy, this guy, and this guy, and I can calculate S sub E. So step one, S sub E is equal to 0.2 minus 0.05 over 0.3 minus 0.05. That's going to be some value.
.06. That's what I got.
Okay.
Or 0.6, sorry.
Yeah, 0.6 makes sense. 0.6. All right, now I need to solve for psi. So I might solve, let's call this 1, let's call this 2, step 2. Solve 2 for psi. SE to the lambda minus 1, or sorry, to the negative lambda. Times, divided by, it's going to be divided by so all I did was take this guy to the negative lambda, this guy to the negative lambda, and then I can see already I'm making mistakes because I'm skipping steps. Let's just solve it. All right. First step, SE to the negative lambda is equal to psi b over psi. I'm going to multiply by psi on both sides, And then I'm going to divide by SE to the negative lambda. So I'm going to get psi is equal to lambda B over SE to the negative lambda. All right, so now I got an equation. I will be given lambda B, and I will be given, or psi B, and I'll be given lambda. And I've got this guy from step 1. And so I can calculate psi. All right, so that would be a pretty typical problem. I might force you to calculate this guy. Could force you to calculate that from some measurements of dry and wet material.
And then, so how does that like relate to the relative hydraulic conductivity?
Oh, well, okay. So I could ask you to calculate B, calculate K sub R. Oh, that's not working. Ugh. Calculate K sub R. All right, so let's find the equation for relative conductivity. So K sub R psi sub B over psi to the 2 plus 3 lambda. All right, so this you'll be given, this you'll be given, and this guy would go in here. So you could plug and chug.
Yeah, I was on the homework I was just confused because like I don't get the right graphs. I already know that, but like were we supposed to like plug in like something like if statements or like some like not just like plug and chug for the problems on the homework? Were we supposed to be using like different? Yeah.
Well, if
because that's what I did, is just plug and chug basically for the homework, and I wasn't getting.
Well, usually if you're not getting the right curve, then that means you got an error in your equation. But here there is a statement, and that is that if psi is greater than or equal to psi sub B, psi is equal to psi sub B. And that's just for the Brooks-Corey equation.
Yeah.
But bottom line is you'll get a in this equation, right, as it's written, you wouldn't have to worry about that. That will only happen when the effective saturation gets really close to fully saturated.
Yeah.
So when this guy's really only when SE is equal to 1.
Yeah. Well, like, for example, like in my homework, if the value I got for relative hydraulic conductivity was greater than the porosity, I would just plug in the porosities for those points. But yeah, I don't know if that was the right thing to do or not, but I was curious.
It's the same here if you're doing Brooks and Corey. If this guy is greater than psi b,
Yeah.
then K sub r is equal to 1. So so you would basically calculate this for all of them, for all psi's until they got to psi sub b. And then after psi sub b, it just becomes equal to 1. But you don't need, I mean, for the test, I'm not going to ask you to do the full curve. You just gotta.
Yeah, I know. I just was wondering what I was doing wrong with the homework.
I mean, I don't,
Yeah.
The Brooks and Corey, I looked at yours really quick. Your Brooks and Corey looked okay. Something's going on with the Van Genukten. You got an error somewhere in your equation. But I won't, for the test, you're not going to have to do that.
Yeah. All right. Well,
Will
thank
you?
you.
Hey, Peyton.
Hey,
Will you post the equations online either today or tomorrow before the test? The equation sheet?
the equation sheet? Yeah, sure, I'll do that.
Okay, thank you. All right, have a good day.
You too.
Yep.